Hello.
Hey,
Good.
oh, I'm so glad, so, alright,
Are you trying
so I have, it shows the audio, but I don't see the video. For this session, till like after midnight, I was a little punchy, that's why I put all the jokes in there.
We'll take her. So some more people are coming, but. I think so, are they?
I'm gonna text Jonathan.
Ah.
But the recording is recording.
Once he gave the talk in 3:12, big,
Yeah.
only Colombia. So I met him there. With one verse, with some jokes.
Yeah.
Very central. You know, what was I? An assistant. Yeah. Yeah.
Well, let's get started, we'll catch him up.
It's also recorded.
Let me
Oh, yeah,
do the right thing first.
please,
Where do I go?
upstairs,
Upstairs.
one
Ah,
floor.
yeah.
One floor, and there's two handicap bathrooms right across from the from elevator.
Yeah.
Ah,
Hey,
good.
Thank God. I was right, I was gonna come in, but the entire board is already gonna be filled.
The suburbs. a little, So I was watching a talk with Terrence Tao, okay?
Like the Lex Friedman one?
Not the Lex Friedman one, it was a talk he gave at UCLA. It was, my attention span is never 3 hours, it's like 10 minutes, 10, 12 minutes is about what I can do. And he was talking about how he used Lean 4. He used Lean 4 to work on some massive proof.
AI or?
No, not AI. So he was talking about actually, we've all experienced it, right? When you use ChatGPT, it can hallucinate, right? It says things that don't make any sense along ways. But there are these proof assistants, and I had always heard about COC, which was developed in France, where it uses the Curry-Howard theorem, which says that basically any mathematical proposition can be translated into a statement about types. And if it compiles, then it certifies that the proof is correct. It may not be the most elegant proof. It may not be the best proof. It may not teach you anything, but it's not wrong. It's not wrong. And not all of mathematics has been certified in this way. And they're starting to do some stuff in probability with Lean 4, which is based on Python, not Haskell, not on OCaml, which COC is based on, but based on Python. And it was originally done by Microsoft Research, but now most of the development is going on at Carnegie Mellon. And I was wondering if any of you had heard about it, played with it at all.
I know that Beam does that sort of thing. I've never actually bought.
Yeah, it's hard enough to keep up with all of this stuff, right? But I was I'm teaching like at a one of those crazy CS boot camps, like if you're willing to sit in front of a computer 8 hours a day, we'll teach you in 6 months how to go from being a musician to being a programmer. And they're all like, and it's like very hard to get hired as a programmer now because like with AI jobs, so everyone's like interested in learning more math. And I was trying to think about like, since they already know Python, like incorporating this in some way, but I wanted to see if any of you guys had used it or had any experience with it.
Short answer no.
Short answer, no, but that's okay. We got more.
Yeah, we got. What happens to physical processes when you reverse time? Before not forward in time, but I think the first guy who asked this question was Boltzmann. He didn't get very far with it because he took his brains out with bullets and then that's a very irreversible. It's a very irreversible form. That was the end of it. But the question was taken up by some of the greats, like Schrödinger. The early thirties. It didn't go more. It didn't go more. It's a very interesting paper. 37. Behavior of random processes or physical processes. Not very much happened with this business in the 60s, in which they did guy very near here in Princeton, Edward Nelson. Oh, a very interesting book. A couple of papers were very interesting. Both the book Dynamical Theories of Brownian Work. And there, among other things, he discusses reversal of time. In fact, the culmination of this lecture will be a formula. And this formula, I like to call a generalized Nelson formula. Because a special case of the formula I'm going to was written by Nelson himself. But even before him, in Japan, Nagasawa, I don't remember the first name, Sawa, starting with 64, long time ago, very long time. He had also wondered about this. Nagasawa has at least one book, I mean, he has written a couple of books. At least one of these two, if not both, discuss cases of reversal of motion. This is one leg of the story. Let me discuss another leg. Very close to how I became probability. The 60s were the decades of Kalman thinking, right? Ruby Kalman was right here at Columbia, in fact, in the math building, which used to be the engineering school. So he studied on the same desks that we have been studying. So what is what is the story with filtering? That we're more serious.
There's more
There's your prayer. The problem of filtering can be a wide problems of prediction. Prediction is I take my time. Okay. I want to do not only this topic, but also the motivation. This is a physical discuss the engineering. Because the engineering motivation sent us to the moon, the Kalman filter, right? Linear quadratic Gaussian control, the Kalman filter sent us to the moon. This was a very big thing. Yeah. Random process. which is your signal. It's a signal that we want to generate here, and we want to transmit it to something. You want to send it either by cable or RFIs. So you want to transmit the signal, and then the signal has to be retrieved. But sending a signal involves noise, right? You are going to get interference from satellites, from the ground, from this, from that. So you send the signal, or at least a function of the signal. Age is a given function. For example, sinusoid, whose amplitude the signal modulates, AM amplitude modulates, or a sinusoid whose frequency the signal determines, frequency modulate. Another thing that happened right here, Armstrong, electrical engineering department, FM, frequency modulation. Many people know it. But an alumnus of the EE department. So this is the signal that we're trying to do. Well, X is the signal that we're trying to transmit, and this function is to modulate. But you can only observe it in noise. Imagine noise. Now, noise is the derivative of Brownian motion, which we know does not exist. That does not stop. That never stopped
an engineer, right?
Right, from writing it down. So, this is what you observe. You observe signal plus noise. Now, instead of appearing like this, you put on a frac, right? Put on a tie. It will behave. If you rewrite this, right? This is what you observe. In other words, the time t, you say, hey, I observe the cumulative effect of the modulated signal plus the standard Brownian mode. This is my observation. So one time you observe concentration after the observation. At any given time, you want to recover as best you can the signal from the noise. What can be more fundamental? And ideally, you say, how lovely would it be if I could characterize the conditional distribution of my current signal? The probability that my current signal belongs to the Borel set A, given the observations that I have received up to time. So the problem of filtering in its purest, most abstract form is exactly this. In this generality, you cannot say anything. You have to start making stronger and stronger assumptions to begin to be able to say something.
The conditional distribution of X with respect to the filtration of Y, right? Because Y, T is measurable with respect to Y.
X.
X.
That's a type. Exactly. That's the X. The X. And in this generality, you cannot say except very general things. You have to specialize. You have to start giving, pretending that you know the dynamics of the signal, and then you begin to answer, you begin to receive some answer. But before I go into that, actually, my biggest regret last semester was that I didn't have time to discuss this. I put some chicken scratches in the lecture notes, but I didn't have time. But before I go further, before I discuss a little more, if I have time, let me mention this. Suppose you say, well, I have my observations up to time t, but I'm not interested to estimate as best I can what the signal is now. I want to estimate as best I can what the signal will be 5 seconds later. In other words, I give myself a fixed number theta, and I say, what is the, when I characterize the conditional distribution of x of t plus theta, given the information up to time. Theta a positive number. This problem is not filtering anymore, it is a prediction. Or you can say, I have collected my observations up to time t, but now I want to go back, since I have observed up to time t, I want to go back. I want to read the movie, right? I have seen the movie up to time t, can I go back to the scene 5 minutes ago and understand it a little better? What really happened? I'm watching Rashomon, right? And Rashomon, you have to pay attention to every goddamn reel that happens to you. Now that I have watched 1 hour of Rashomon, can I go back 20 minutes and understand that scene a little better? So I'm going back to Kurosawa, turn the reel backward. Now, in the old days, you had to really turn the, and now you just press the rewind button.
But just on I guess I'm thinking about it in terms of telecommunications.
Yes, yes.
So what you're doing is you're observing theta, and then
No, I'm not
on-
observing it. I'm fixing.
you're observing
Why?
you're observing Y.
I'm observing Y.
You're
I'm observing a function of the signal, frequency or amplitude modulated or anything that you want. And I
Right.
want to recover the distribution of x of t.
I guess I'm asking is you're smooth. So when I'm listening on the receiver, right?
Yeah.
The filter is making its best guess of what the signal was some buffered distance in the past.
Yeah, when I put minus sign t. Yeah. And now it's not filtering, it's not prediction, it is what we call smoothing. But the moment you formulate this problem, you are doing time reversal. You are going to Rashomon, right? You take the read and you go backward. You are reversing time. And in the 60s and 70s, there was a lot of effort to understand not only the theory, but also the theory of prediction, the theory of prediction, and of smoothing. But the moment you write down the smoothing, you are asking about reversal of. So that's why a lot of engineers, among them, Anderson, Canberra, David Castagnone, you both of them in 82. Ask the following question. What if you give me a diffusion process? Give me a diffusion process X. This is the ratio of time reversing its purest form. Give me the diffusion process X. Give me a time horizon 0 to capital T. Describe for the previous the nature of this process. That's the smoothing problem in its purest form. Time reversal. If I know the dynamics of X, what are the dynamics of X capital T minus? I remember those two guys, those days I used to go to the local for electrical engineering. Back in 81, 80 or 81, I remember both of them talking about this subject. So they wrote, both of them wrote their papers in 82, I mean, published their papers in 82. Already, up until that time, another guy in France, Etienne Pardoux, a very good friend, was working on these problems a lot. And I just trying to understand these two papers, Pardoux and Ulrich Hausmann. Although the very influential paper, 86, annals of probability. Time reversal of the truth. All the theory is there. There's only one catch. No one can read the paper. Not because the mathematics is not correct. They are excellent mathematicians both. It's just a very bad reading. So, despite the fact that everybody believed what they were doing, this is it. You cannot read it. It's boring. And then, in situations like this, you need a Deus ex machina. And in this case, the Deus ex machina was one of the greats, Paul-André Meyer himself. So Paul-André Meyer himself, the great guy, successor to Tour. If anybody can claim the mantle of Tour, he can. He wrote the 3-page paper. Of course, in the publication, Friends and Relatives, 1994, a magnificent paper. In which he explains in crystal clear terms what's going on in them.
Should I post the 1994 paper?
I'll send it to you. It's beautiful exposition and beautiful friend. If you are into that kind of thing, it's so magnificent. So when I saw that paper around 94, 95, I got hooked. So my own interest in time reversal and kind of resurrected itself with that paper. And the notes that I have follow what Paul-André Meyer writes, they are kind of slide. So let me try to explain what how Paul-André Meyer understood the world. Hausmann and Pardoux, that no one can figure out. Speaking of this, if I give you a Markov process, the reversal of the Markov process is also a Markov. The Markov property is invariant under time difference. Past and future are interchangeable with the definition of the Markov property.
Right, the subtlety is that the strong Markov process doesn't
Yeah,
always. hold.
then you say, if the Markov property is invariant under time reversal, how about the strong Markov? There the answer is in general. Yes, under conditions, but in general, no. Then you say, how about the semi-martingale? There again, the answer in general is and the reason is that if you allow yourself to go into the future and come back, for certain purposes, you may have already learned too much. Remember that movie, The Man Who Knew Too Much? Eh? You know what happens if you know too much? Yeah. You may have learned too much, and that destroys the Markov code. And yet, for fairly general diffusion processes, in other words, under good conditions, believable, reasonable conditions on B and on sigma, the time reversal of this diffusion process, not only is it a Markov process, not only is it a strong Markov process, it's also a diffusion. And not only is it a diffusion, you can characterize the drift of this diffusion, you can characterize the dispersion. The dispersion stays the same, but the drift changes. And it changes according to the formula that I mentioned before of Nelson. The formula that Nelson first wrote down back in 65, 67. This formula allows one to recover in much greater generality. I'll try to write it. Everything is a lot simpler. Everything that I'm going to present is a lot simpler if you assume that sigma is identically equal to 1. But the interesting probability comes when sigma is not identically equal to 1. So in this case, I'm going to go for generality rather than concrete. I try my best to describe why the general case is so much more interesting and how the formulas look in that more general. Derive the analog of the Nelson formula. I don't know how well I'll do, but let me get started. Yes. Let me erase everything. Take a look at the filtering nodes. I don't know. I hope at some point you can go over them. They would have other fish to fry. The next leg of this story is in our case. Nowadays, time reversal is huge. AI image generation or restoration, so on and so forth. I'll discuss that when we write down the Nelson formulas in the very special case of larger dimensional reports.
We're gonna use the innovations process.
No. The innovation process plays is huge in context of filtering. Here, no, we're going to use something else. In analog of the innovation process, you'll see, yeah, that's a very good point. If Brownian motion is going to hit us in the face, but it will not be innovation, it will be addressed in a different government. Again, it's going to be a fundamental part. Under a different filtration, exactly like the innovation. So it's yeah, we are going to see a glorified innovation. But the context will be a little different. Very good point. Very good point. So multi-dimensional diffusion. Eventually, three-dimensional Brownian motion. This is the new component. W nu, W1, WL, W3. Nu is the right. This is for every I one down to three. C is the initial condition, random variable, and W is an independent Brownian. And I'm going to assume that you have all the good conditions in the world that guarantee that this equation is a part-wide unique strong solution. So you give me the initial condition C, you give me the Brownian motion, I generate the solution. The solution, of course, is adapted to this equation. You give me the initial condition, you give me the path of the Brownian motion up to time t, I can generate extra. Provide the filtration. This is the same equation as the one generate. C by X of theta and W. I'm going to write a few equalities. And at each stage, please tell me whether you believe them. In other words, if I know them guys, I know them. If I know them guys, I generally the same thing. Or I can write it like this. X0 is the C, thank you very much. Now I say, I don't want the Brownian motion, I want the increment of the Brownian. That's simple. I know the Brownian motion, I know the increment, if I know the increments, I know the Brownian. Why am I doing all this nonsense? Doing all this nonsense because I want to press the point. Two equations generated by two things. The initial condition and the Brownian increments between times 0 and 1. So G of T is the sigma algebra generated by these. Do I have a word? Okay. Now, I am going to assume not only that this equation is the pathwise unique strong solution, but that it also has a probability density at all times. In other words, I'm going to assume smoothness condition. The distribution at time t of the solution is a probability density. A is a Borel set example. And this is a probability density function which satisfies which equation? It's a function of time and space. It satisfies which equation? The forward Kolmogorov equation, Fokker-Planck, and the backward. I'm going to assume that these equations, and you can open the books, you can find only sufficient, of course, conditions under which these things to assume enough smoothness and flow conditions on the definitions that guarantee solvability. So just to add something, let me write the formal Kolmogorov, the Fokker-Planck. This matrix always goes. This is the forward Kolmogorov. Second derivative of the product. What is Aij? You have the dispersion matrix, it's a D by D matrix. Then you look at this matrix, sigma sigma transpose. That's the local variation matrix, sigma sigma transpose. And this is the Ij from the
And S, same thing as sigma. You wrote that, the dispersion matrix.
I only have S2.
What is S in terms of the dispersion?
It's a dispersion.
Okay.
Now I call it S.
Okay.
I call it sigma before, I call it S now. According to S. This is the Fokker-Plackett way. If the B's and the S's don't depend on time, then there is home that this equation is a stationary solution. In other words, that as t goes to infinity, there is an invariant measure, and this measure is a probability density function. And if all is blessed and goes well, then this invariant probability density function satisfies this equation. This becomes zero, right? And this becomes just a function of x. This becomes just a function. This is the stationary version. So now I say although I have watched the movie up to time capital T, now I reel backwards, right? Or I press the button the backward direction, and I look at the movie going backwards. Then what do I see? Oh, I see this one. What kind of process is it? Well, first of all, let me write the analogs of this. I'll be a little pedantic, but I prefer to be pedantic than okay. So let me write. Yeah, this is a separating line here. So let me write F capital. I'm imitating this. Imitating this. The essentially like this. Okay. So I look at exactly the same objects, except now into the future. Time t, I say, let me look at the values of the process x of the Brownian increments into the future. After time. This is the same item because the equation is the path lines unique on the. This is the same as this. It's the same as this. Give me the position at time t and all the future increments. then I generate the entire process into the flow. Or to give it a terminal position. And go the future increments, and then I generate the same process but going back. But now, I write this in the orange form. What is the orange form? The exact analog of this. Where calligraphic H is this. Calligraphic H of T is the sigma algebra generated by all the increments of the Brownian motion from time t to time capital. You see the exact analogy, the exact sample. Forward and back. Backwards increments, forward increments. But now I remember this. So now I index not by T, but by S. So here is now my new guy. Here are now my two increments. The gentleman. The kindergarten or class semester. Brownian motion. If I have Brownian motion and I reverse time, what do I get? I get Brownian. So I look at W tilde, which is the reverse Brownian motion, and I look at X hat, which is the reverse solution, which is the reverse solution. And then I index time not going forward, but going backward. So I rewrite this. It looks a little pedantic, but believe me, it takes. You cannot imagine how long it takes to get the notation right. But then you get the dividend. In other words, how far can I slow?
Till the end of the sport.
Right all the way to the corner.
Let me. You will remember this.
Yeah.
Let me write here, because then we have a one-to-one correspondence forward and back. Blackwood management is a lot.
And we limited you very,
You learn it by doing it. Yeah,
this room is great, but it's
Yeah.
very small.
yeah, it's a space, yeah. So I rewrite there, now, you remember F hat, I rewrite F hat, but now with time going backwards. So I replace little t by capital T minus S. So allow me the pedantry, allow me the pedantry, x of t minus s W for T minus U, let's say. So I replace theta by T minus S and T minus S. Yes, and T by T minus capital T minus Q. Now U travels from 0 to S. This is just a rewrite of f hat of t, but now with time reversed. Instead of little t, I have capital T minus S. This is the exact analog of that. Don't like this. Just a moment. Don't like this. This is Q. This is Q. I replace theta by T minus Q. Forgive me. T minus Q. T minus Q. Then little t is T minus S. Sorry. S. T minus S is little t. And T minus U is theta. Now I have it wrong. In other words, what is x of t minus u? X of t minus u is x hat of u. And what is this? That's the increment between S and U of the time reverse down. And then I observe by analogy with this, I can write this sigma algebra is the same as x capital T and then the same increments. In other words, when I look at these increments in the value of the process at T minus U, I generate the same filtration as keeping the same increments in the value of the process at time capital T. Exactly the game we played above. But x of capital T is x tilde of 0. What is this? Filtration that I like is H of T minus. Exactly this, but now with time 21. H of T minus S is the filtration generated by this. The same as the filtration generated. The increments on the backward come. huge observation. This is, we said before, what is this? If I reverse it, Brownian motion, I get a Brownian motion. But now I go to the next question. With respect to which filtration? In other words, every Brownian motion is a martingale, but a martingale of what filtration? Well, of it, the filtration itself generates, and of every smaller filtration to which it is adapted. If you give me a process and you tell me, this is a martingale, I have to ask two questions. What are the two questions?
What's the probability?
What's the probability measure
and
and what's the filtration? Well, if it is a martingale, it's at least it's a martingale definitely with respect to the filtration that it itself generates. And it's also a martingale with respect to every filtration which is smaller and to which it is also adapted. But then you say, if you give me a larger filtration, the Brownian motion is also adapted to that filtration. So it should be a Brownian motion with respect to this larger filtration, right? Wrong. Wrong. If you enlarge the filtration, the martingale, the semi-martingale property is not necessarily present. If you decrease the filtration and you keep the semi-martingale adapted to it, then you keep the semi-martingale. Martingale and semi-martingale. But if you enlarge the filtration, you may lose the martingale property and you may even lose the semi-martingale.
There's a much.
Exactly. Yeah, because
That was what when I was saying, like, that was the part. How do you know too much?
I'll tell you in this case what goes.
I can't think about enlarging the filtration, the entire system.
Yeah, you enlarge the filtration and somehow the information structure changes. And some properties may get preserved, others may be lost or modified. In this scenario here, in this story here, this process is Brownian motion. Brownian motion is a concept that does not involve. What's the definition of Brownian? Continuous path, so it does not involve any filtration. So when I say this is a Brownian motion of this filtration, what am I really saying? It is a Brownian motion, but it's a martingale with respect. I'm specifying the filtration with respect to which it is a martingale. So when you hear me say this is the Brownian motion of this filtration, I'm saying really, right?
It's measurable and
Yeah,
adapted.
yeah,
with respect to
adapted,
itself.
yeah, exactly. Yeah, the martingale though, saying that it is a martingale with respect. That's what I'm saying. So this process here is certainly a Brownian motion of this filtration. But that does not mean that it is a Brownian motion this larger. This filtration here is this plus that generated by the increments and by the initial condition. The initial condition for the which is the terminal condition. So the fact that this process is Brownian motion with respect to this filtration does not mean that it is a Brownian motion with respect to this one.
Okay,
In fact, it is not. That's the bad news. What's the good news? It is still a semi-martingale. And not only is it a semi-martingale, we can write down the semi-martingale characteristics. That was the ingenious thing of Paul Dremeyer that was lost somehow in the analytics of Pardue and House. Right. They couldn't quite master the strength to make it that simple. Yeah.
So we're looking at the time reversed Brownian motion, which is a Brownian motion with respect to the h.
Yes, but not with respect to this.
To h of t, little t, but not. Okay.
Yeah, to this situation. But not with respect to the larger.
Okay,
Okay.
so, sorry,
We have to understand this.
yeah,
This is the crux of
yeah,
the story.
so if I know X had 0, then I know X
Time capital.
had time capital P. Which I'm thinking if it was a stopping time.
I'm a prophet.
You know.
I'm a prophet. I'm a prophet.
You know that it's stopped,
Yeah,
whereas by X T minus U,
yeah,
I may not know that if it stopped, so I didn't know if it ever stopped.
exactly. Exactly. So the backwards filtration, F hat of P minus S, is generated by X hat of 0, in other words, by the terminal condition, plus the increments, the Brownian increments. The increments of the W tilde process. The W tilde process is a martingale with respect to the filtration generated by its own increments. Thank you very much. But if I enlarge it by the terminal condition, which is the initial condition of the backwards process, it ceases to be a martingale. But it does not cease to be a semi-martingale. And then you say, if it doesn't cease to be a semi-martingale, what is the semi-martingale become to? And here is the mastery of Paul Dremeyer. Okay? So let me give you the semi-martingale decomposition. It's like this. This is a small cube. They're not exclusive. Different. Questions? Which I'm about to write. the nth. What is P? P of T and X is the probability density function of X of T. What is sigma bar nu? Sorry, S. S is a matrix. Which has entries Si nu. So S bar of nu is the column vector at the end at the node entry. The node column of the node. And then you take the divergence of this vector with this, well, you multiply this vector by that scalar, you get a vector, then you get the divergence of this vector, and then you divide by P. So you assume, for example, that P is strictly positive on the entire spectrum.
Is the S matrix where you have the dispersion?
Yes.
Yeah. Yeah, that's the S matrix, and this is the node column. It's a vector. Multiplied by a scalar, it's another vector, you take the divergence and you normalize.
Sorry, one more notation.
Yes.
The bar is because. Oh,
Just a notation,
oh, okay,
it's just a notation.
It's not a
To
complex
remind
application.
ourselves that we're dealing.
yeah, or time reversal or
Yeah.
that,
No, it's just,
Just vector.
just vector.
Vector.
let's make it a vector. A true vector. Complete the sentence.
So you integrate it with respect to the time reverse process, which
Yes.
is x hat
Yes,
time.
yes,
Reverse time t minus u.
yes, but complete the sentence for me, what does the theorem say?
Brownian motion.
Brownian motion,
Respect
it's
that.
Brownian motion with respect to it.
That's the.
Which tells you that W tilde itself is a semi-martingale with B as the Brownian component and the other guy as the finite variation. Poor Hausman and Pardue. They struggled after dozens and dozens of pages, but could not see it.
We did that.
Maybe four. Yeah, it's something else. Yeah, then you look at that and you know you're dealing with a master, right? Yeah. Yeah, everybody was, oh, this great work of Pardue and Hausman, and we don't understand it, what the hell is going on? And he sits down, everything becomes trivial. Brownian motion of the equation that had or T minus is you think this is good, it gets better.
Okay.
Let me almost. Well, let's segregate this result because at some point we have to do it. But before we prove it, we want to tell you what it is. Some of the things we did. This is the crux of the whole thing. There is more work to arrive at where I want to arrive. But this is the crux of the whole thing. Now let me do some silly manipulation. We look silly for a while, but then we'll see where the silliness will be. Let me write. Let me evaluate this at time t minus theta. Let me evaluate at time t minus t. Subpart. So in your mind's eye, write this expression this time, write this expression that time, and then subpart. This is an increment of this number motion with time reverse. I'll reverse time again. So I keep reversing time. Right. Which process? Which I give a name. We call it V nu of T. I ask you to believe. To repeat what I do here, but make yourself this relax. What is this?
First time twice, you.
Yeah, Brownian motion. It's a Brownian motion. Oh my God. And now I ask you to be indexed by little t. This is Brownian motion. Now suppose that S is identically equal to 1 and B is identically equal to 0. In other words, I have just Brownian motion. Then what becomes of that? Well, I know the transition probability. It's a Gaussian transition probability, right? I do it in one dimension, S is 1. What do I get? I get this. What have I proved? If W is Brownian motion, so is B. Remember that exercise in the lecture, no? Not yet, not quite. No, no.
It was a
No, that's
standard proof.
Yeah, that's another one. It's another. Brownian, we'll see. The Brownian bridge will hit us in the face, but this is not it. Something else entire. It's the Brownian motion of Jelen and Euro. Jelen and Euro, our friend. Euro. Yeah, the moment you see this, your jaw drops. Why should this be even well defined, let alone Brownian? Okay. Okay. Enough. Let's see if we can prove something. We need space, so I leave statement of the calculator. Pass through this. Okay, get it. The year starts with this very humble observation. Give me an integrable quantum variable, kappa, which is measurable with respect to f hat of t. Then the conditional expectation of this kappa given f of t is just a conditional expectation given x, the value of x at time. If you believe it, that's why you believe it. Here we're using the mark
K is measurable with respect to.
f hat. That's one observation. The other observation is that if you give me now function g. Very smooth. Very compact with something. And you can define function leakage. Of g. or define this function as g of theta x, and this interval goes out v. Then I asked you before, what is this? Well, they say I'm just a boy from the village, right? I just rewrite what you gave me. Now I remember that x is a, you said it, Markov process. What I say about it? It's true. It's the conditional expectation of some random value, given f of theta. Is theta travel between 0 and the definition of the one. But if it is a martingale, and if, as I can apply Ito's rule to it, I know that something is going to be 0. I hit this with Ito. Nobody can stop me, right? It's my privilege, if not my right. Yeah, I can hit this with Ito, but then I know that because it's a martingale, the bounded variation part in the Ito decomposition is going to vanish. Don't tell me this is a very deep observation. So I can write this, in other words, as a stochastic integral with respect to the problem. Don't tell Ito. Except I don't even bother to write anything else. Because I know it's going to be 0, so why write?
One
Yes,
parenthesis
yes.
on the right hand side.
well, it seems that I'm missing something, but what I'm missing is g of theta x theta. But the product of g of x theta with this increment is zero. Now it's correct. But I claim this is it. Why is it so?
The Brownian motion has a dependent.
Exactly. Because the Tower property, I condition with respect to f of theta, this is measurable, but then the conditional expectation of this with respect to f of theta is zero. I don't bother to write this. But now what is this problem? Well, this difference is this stochastic integral. I take the inner product, of this stochastic integral with the Brownian income. What do I receive? The integral of the integrand with respect to the bracket. So W with itself. So in other words, dt, dv, whatever, but only of that component. All the other components are zero because of the independence, the independence of the Brownian component. In other words, like how right, the expectation is an integral with respect to the probability density. So now on we do analysis. What do I do when I have a differential operator like this? integrate by parts, right? The last resort of this country. I don't know what else to do, I integrate by parts.
Perfect. So on the previous line, so we have the right at the end of the previous line, we have the expectation, the next equality.
Right, inside of that. Well,
Yes, the dv should be a dw nu v, right? Or my,
No, I remember that,
it's just dv.
yeah,
Because I thought the finite variation, which is the second derivative, would vanish, but in the first derivative we had dw, right?
I think of dv
Hmm.
is d.
Just right above it we have dw.
W.
Hmm. Uh-huh.
That dv.
Oh,
So the v comes from the quadratic variation of the news component of the power of motion, and all the other force products are the. That's why only the news guys survive.
okay.
This is what I call. This is the divergence, right? This is now the divergence of P. Exactly the divergence. I have to sacrifice the summation. Sacrifice the summation, and then the summation of all these guys gives you the divergence. And then I divide by P of V and X, multiply by P of V and X, dx. And then what I receive is minus the expectation. This brings the expectation. Of what? The G times the divergence. Now I remember the definition of G. And I rewrite this vector function. This line, I want to do here we are. What we have to do? Now I combine the first guy and the last. See that I could prove the following. Take the first and the last. Now I need to prove it like that. All I need to show is to show that this B is a martingale of this conclusion. Because if I show it's a martingale, it will also have a quadratic variation. But you can only inherit the quadratic variation from this. The quadratic variation of this can only be one thing, namely T, because this is a Brownian. All I have to do is prove that this is a martingale of nothing. In other words, I want to show this. Is zero for every kappa log. I write this difference in terms of the W. I write this difference. I write now. What is kappa? Kappa is like this. And what is this? This is FT measurable. This is this wall, this entire thing. It's FT measurable. So I can take conditional expectation given F of T. But what is this conditional expectation? Of X of T. It's F of XT measurable for some bounded function G. This is what did I do? Definition of Taylor property, definition of conditional expectation, if you marking if you marking grades and integration. I only have 10 minutes. So I can only stage the big result. Don't get back to prove it, but this is. Here, the year does 2025 pages. If you and then it's just manipulation. Manipulation. Which is completely trivial if the cipher is like 2021, which is the primary issue with panel. Using this. Vector, matrix, vector. 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 Which value of motion? E.
That's x hat of s.
Not notation.
U.
This one. Yeah.
And du in the drift.
Same distance. Same distance. What if? Let's click now. With a few manipulations, integration point. And something more, but the something more maybe we leave it for another time, which was question. Drift of the forward process. Drift of the backward process.
Fs.
S transport. Probability density function. Solution of the forward. I need to give meaning to this. This is a fantastic model. Comes out of this analysis. Fixed I. I take the derivatives, partial derivative. It's J. And when I look at the question.
Also taking the vector of the divergences of columns.
Yes.
This is the generalized Nelson.
This is the generalized Nelson. Sorry. This is the generalized Nelson. Take the divergence that you see here. And then I look at this vector multiplied by. Special case. Multiply vector down and We can just run that motion. I know what is. C is my initial position. This is the probability density function of the Brownian motion at time t started with position C. I take the logarithm and I can differentiate, take the gradient, differentiate with respect to x. These are childish things. So I'll do them. And I write down the dynamics for the time reverse project.
Oh my.
What else can it be? It has to be the Brownian bridge. Because if you go backward, you have to.
You have to force
You
yourself.
have to force yourself to the starting position. And how do you force yourself? Brownian bridge. Now, as a result of this, trifluid kind of thing. I will say this is for kids. We want to play with a big boy. Okay, let's play with the bigger boy. So we look observance for the post. Well, for measurements for the post. We know that this guy is an unnormalized, say, invariant probability measure. Invariant measure, unnormalized invariant. You normalize it, you make the problem. And then we look at the likelihood ratio. And if you start at the invariant distribution, you stay at the invariant distribution, so this likelihood ratio is constant. You know what becomes of this? Exactly what I had written down the slides. That I presented in the class. Logarithmic gradient. This is what I use here at it's attractive. Of course, if you start with invariant distribution, then this is going to be constant. And the derivative is going to be zero. So you are going to have the exact same dynamics. Which answers, of course, the question of both. In this case, the forward process and the backward process have exactly the same dynamic. If you don't start with invariant distribution, you are going to see different dynamics. And in image generation, you don't want to start with invariant. You want to start with an average. Go back and sample from it, create something from it. So there you have to solve the Fokker-Planck equation. But we have some idea how to go with that, how to compute the semi-group in your field larger than diffusion. So we have a chance at writing down these things to put in this. Well, 2 hours was not enough to complete the theory, but if you read a couple of pages, then you have to complete. We need to find another volunteer because I have reached the limits of my exhaustion. Okay, then we need to, we need someone else to step up. Because I doubt that I will have enough energy now. Things are piling up on me in many directions. So we need to figure out a topic of the volunteer.